Alright guys, good afternoon. So today we are going to move sort of to the next part of what we've been talking about with bolts. So yesterday we talked about the bolt diagram and the bolt equations. So basically how do you handle when you've got initial tension in a bolt. Today is all about, alright, now how do we analyse fatigue for bolts? So hopefully you'd be confident enough to analyse almost any static case with a bolt. When you have a free tension, effectively all we care about is the axial load in the bolt, assuming that you can prove that there's, that you don't have separation and that the shear doesn't get dumped on and that sort of thing. If there's no free tension, then we've done static loading for that. But for the case of fatigue, we need to do a couple of little extra things. Alright, so it's pretty much the same procedure that you've been doing for fatigue thus far. I'll say first, this first slide is for the case of no initial tightening. It'll be pretty rare to have a bolt under fatigue that doesn't have initial tightening on it. You do that initial tightening to remove all of those other complexities of shear stress and all of that kind of stuff. So if there's a chance that any of that stuff's there, you would almost always specify an initial tension on that bolt. The other reason is with fatigue, if you've got static loading on a bolt, fair enough, it's not highly likely that that bolt will actually loosen itself. But if you've got fatigue loading on that bolt, then the actual nut will want to work its way off, and one of the best ways you can keep a nut on a bolt is to actually have that pre-tension holding it nice and tight against the threads. Alright, so among other reasons, the reason that we'll have pre-tension for fatigue case in almost every circumstance is to maintain that actual tight nut on the end of the thread. But just so, sorry I've got a cough voice so I can actually talk today. Just so that you're starting to understand where we're going, this is the case of no initial tightening. This is the diagram I showed you yesterday where our plates would go, the force of the plates is zero obviously, and the force in the bolt is just equal to whatever your externally applied load. When you have a case of fatigue, you're not going to be told the maximum and minimum force on a bolt, you're going to be told the maximum and minimum force on the machine component. Alright, so the maximum and minimum force that you'll know will be whatever's on the actual machine itself, not the bolt. You need to calculate the load on the bolt. If you have no initial tightening, it's very easy because whatever the external load is, it's just equal to whatever the bolt load is, and you can go straight from that diagram. And so if we had the case of the external load going from 0 to something, then over here we've got our force first time. You just be going, force in the bolt is going between 0 and something. Okay? And that just projects straight off that curve there. If you had the case of our external load going between some min and some max, once again, min projects across, max projects across, and you've got your fluctuating load up there. Okay? And so if you know your min and max, you can work out your A and M. You can plot a point on the AM diagram and you can work out how close to the line you are, or whether you're inside, outside, so forth. Alright? Now it gets a little bit more complicated than that because we can't just trace a line from the origin through our operation point and calculate our factor of safety anymore, but I'll talk about that. This is just sort of a starting point to start you thinking about fatigue. Alright. Now this is where we're actually going to live for fatigue for bolts. Alright, it's going to be, as I said, very rare that you have fatigue on a bolt that didn't have an initial tension. So if we have an initial tension, an initial tightening, whatever you want to call it, then obviously our bolt diagram comes into play, our bolt equation comes into play, and now we need to think carefully about what the actual forces in the bolts are. So similar circumstance, let's say that our externally applied load is going between 0 and some value. Alright, now instead of just calling that bolt load, we have to calculate the bolt load using our bolt equation. Alright, so on the actual diagram, these would project up and you're actually travelling between these 2 points, and that's your fluctuation. And so your maximum bolt load is Fi plus, the KB divided by KB plus KC times Fe or whatever. Alright, so your maximum, the Fe you use in that equation is Fe max. And your minimum, the Fe you use in that equation is Fe min. Alright, in this case, if Fe min is 0, it just means that this part is 0, and all you have is Fe equals the initial force. So, if your externally applied load is 0, obviously the load of the bolt is just whatever you initially tighten it up to, and then as you add external load, you'll go from tightening force to more of a tightening force again, and that'll be your fluctuation. Okay. Now, for a second case, you might have some non-zero Fe min and some non-zero Fe max, and it fluctuate between those. And once again, you can project it across, and in this case, you actually have to use the whole bolt equation for the min value of bolt force and the whole bolt equation for the max bolt value of bolt force. Alright, so it seems complicated, but it's just those equations. You're just actually working out where you are in space, or where you are, particularly relative to this S point. Alright, so this is assuming that both maximum and minimum are to the left of that S point, and most of the cases they will be. If it's a really bad design and one of the forces is to the right and one of the forces to the left, you need to know about it. Because at that point, it looks like this. So maybe track there or somewhere in here for the min point, track there for the max point, and so you have different equations here. Obviously at the max point, the force on the bolts is just equal to the externally applied point. And the min point, if you're to the left with the min, then it's the whole bolt equation for the min value. And I suppose the last version of it is if both max and min are to the right of the separation point, then you don't care about the bolt equation at all anymore, and you go back to square one. Alright? But this is uncommon because it's bad design, because there's no point actually having initial tension in a bolt if you intend to load it up such that you get separation. Alright, because as soon as you do that, either your gaskets failed, or you've lost your shear carrying capability, or you've lost, all of the different advantages that you actually have. But, I might put the cat amongst the pigeon and actually make you check that you're left or right of S there. So that would be probably the only circumstance if I was just trying to be tricky in a quiz question. Cool. So that's how you're getting your max and min bolt force. Alright, so it's what we did yesterday. It's you're just thinking about 2 points, a max and min point, rather than just 1 point, an operation point. Yeah, but the procedure is identical. You just take your one value, you think about where you are in relation to separation, you make sure that you have your initial tension and all your stiffnesses and so forth, and then you calculate, and the same thing for the max value. And then, an equation that relates max and min to A and M. You can either do that on the force, or you can do that on the stress once you calculate it. We've only got axial load, which we're pretty much assuming all the time with fatigue. You divide F by A, and then calculate A and M from there. And once you have A and M, you plot it on an A and M diagram, and you do everything that you've done so far. Cool? So it's pretty much the same. Now, the one complexity with that, or I suppose two, one, we've got to calculate the SN. SN, again, we have a couple of little differences like we did for welds. So I'll list those in a second. They're not real differences, just things that we can or can't get rid of. And the second thing is stress concentration. Now, anyone that skipped ahead in the textbook will have seen this table for bolts, for stress concentration. And now that's giving you your KF value, and remember that up till now we've been applying that KF value to the stress side of the equation. And now that gets a bit tricky with bolts, and so we're going to take it over to the other side of the equation, but I'll explain that in a second. So just for starters, 4 numbers. That's all we need. Right, so for class 5.8 and below, or for if you're dealing with imperial, United threads 2 and below, there's 2 different categories, roll threads and cut threads. So that's just 2 different ways that you might actually get, those threads. Now, cut threads is something like what you would use a tap set. So you're actually cutting those threads yourself. And obviously, because that's just a fairly simplistic manufacturing process, that's potential to leave, chips and jagged edges and that kind of stuff. So inherently, that's going to leave more stress concentration and potentially worse surface finish than nice rolled threads, which is the way that you actually manufacture threads if you're mass producing things like bolts. So the majority of your off-the-shelf bolts would be a rolled thread. If you're cutting the threads yourself or there's some sort of custom bolts, then it might be the case that you've got cut threads. Cool. And then for the stiffer stuff, so 4 and above and 8.8 and above, 3 and 3.8. Okay? So you just use a single value, you've got KF, and you carry on your merry way. Now, this table, because you're actually dealing with manufacturing processes as well, these values incorporate a surface finish into them. Okay? So you don't need to get a stress concentration factor and a surface finish, because theoretically the stress concentration and the surface finish are all part of the same process, and so that's been incorporated in these particular numbers. Now, theoretically you take that KF and you multiply it by your stress that you calculate and you go on your merry way. The problem with that is that we have a pretension, and our pretension, we're ramping it up almost all the way to yield anyway. Alright, and so that's static loading, but we're ramping it all the way up to yield, and then you multiply it by 3. And so you've already failed, which kind of invalidates that process. Right? But let's think about that for a second. What happens to stress concentration in static loading? Remembering that initial tension is static loading. If I had a stress concentration of, let's say, 3, and I statically load something, we have that localized yielding in the stress concentration zone, but the rest of the cross-section hasn't yielded, and as far as static failure is concerned, we're still okay. And that's why we didn't really use stress concentration in static analysis of the bolts, because stress concentration isn't critical for ductile material for all the reasons that I told you when we were initially talking about stress concentration. Alright, so theoretically, it would yield locally at that initial tension point, but the rest of the bolt wouldn't have an issue. Now, if you're talking about fatigue, stress concentration is very, very important. Alright, so if we just blanket apply stress concentration to the stress and assume that that's correct, then that static loading part of it is going to be invalidated because we're going to shoot off to the right. What we actually do is just apply stress concentration just to the fatigue portion, and we can do that by doing that on the SN value rather than the stress. And I'll show you that on the next slide. Right, so these are our endurance limit modifying factors. So we've got axial loading, so the first one's CA equals 0.9, which is the same value for axial loading that you've been using. And the second value, surface factor, that's where we're going to actually use that stress concentration. Okay? It's a little bit different to previous years. I had an actual, a separate thing, and you just use one for that, but just ignore the previous notes. There's a few extra factors in previous year's notes, but it's exactly the same. Alright? So surface factor, because KF's dealing with both surface and stress concentration, we're going to throw it in there. And the way we calculate that is just CV equals 1 divided by your KF value. Okay, so the KF that you calculate. Now if we think about just the fatigue case, right? So just fully cycled fatigue. Remember our stress, what do we need to be? Less than or equal to SP on N. That was our equation for that case. Right? Now theoretically what we did was what I've got here, which was this value was actually KF times sigma nominal or whatever, and we were saying that was less than or equal to SP on N. Now what I'm saying is that we can take that, divide both sides by it, bring it down the bottom here. We've got exactly the same equation, it's just we're putting it in a different place. Right? So that's what I'm saying here, that if we use 1 on KF here, it's exactly the same as saying multiply by KF on the other side of the equation for the fatigue case. But what that does is it localizes it just on the fatigue value of stress, and the static value of stress now doesn't have a KF factor. Right? So if you think about your AM diagram, effectively what it's bringing down, This is our AM diagram, right? If you apply that KF on the stress, let's say 3, you're bringing that down by 3 and bringing this in by 3, like that. Which is fine for all of the loading that we've been doing because we haven't had any pre-tension and things like that, so to be nice and complete, it's fine to do that. And it was a lot easier to apply it to the stress when we have multiple components of stress and different stress concentrations that result. So it's a lot easier to apply KF to the actual stresses for most cases, but because we just have axial load and a single KF value, that's not as convenient for this. What we're actually talking about with bolts is, now that we're only applying it on the fatigue side, we're effectively bringing that, if it's 3, bringing that down by 3, but we're not doing anything to that other end. Which means that when we come over here on our pre-tension, we've not screwed everything up. So if we did this and came over here on the pre-tension, we're already counting that as failed. Okay? So because things yield locally and say yield isn't a big issue in static failure, we can actually do that and just apply the stress concentration to the fatigue side. Now, your textbook does it a different way. Feel free to read that chapter. I read it about 5 times and I still don't particularly understand it because they kind of do crazy stuff where they actually do it this way. But then they say when you initially load it up, it will reach yield locally, so we'll ignore that and then we'll track the line up here and then we'll ignore that and then we'll unload it down here, and it's a whole extra process that you go through just to work out what the factor of safety is, which pretty much gets us to the same point that I'm saying here, except my way's a hell of a lot easier. So read that section in the textbook. There's always multiple ways in design of actually doing these analyses. Alright, lots of different textbooks approach it different ways, and some are a little bit more conservative, some are less conservative. This one's about the same in terms of quality of result, and it's a hell of a lot easier to implement. And so that's why I've been teaching it this way for however many years. And really the only confusing point is that we've been using KF on the left up till this point, and I'm asking you to use KF on the right for bolts. Okay, does that confuse the hell out of everyone, or are we on board with that? Feel free to use it like a black box. And if you want to understand it more, come and discuss it with me. Okay? So all we do with bolts is we just calculate our KF and we throw it in this parameter here. We carry it in our merry way, and that takes care of your stress concentration. That's as much as you need to know to get good marks in this subject. Cool? Very good. Alright, temperature factor exactly the same, reliability factor exactly the same, miscellaneous exactly the same. So you guys are across that. Really the only complexity is how we deal with those stress concentrations of the threads. And that's only a problem because you have a pre-tension, which makes conceptually things more difficult. Alright, last thing, AM diagram. Where's your load line locus and how do we calculate factor of safety? Remember, the first factor of safety we used for bolts was that separation of the plates. Alright, so that's one factor of safety. This is the second factor of safety, so is our bolt actually going to fail? Alright, and then you choose the lowest factor of safety, or you make sure both of them are within your bound or whatever. Now, we have a pre-stress. That pre-stress is static, and that pre-stress we assume is there for the life of the bolt. Alright, so once you ramp that up, that bolt is there for good. If you don't have any applied load, that's effectively a static loading, so all sigma M, no sigma A, and we are at whatever point that is. So 90% of proof load, then that's that value of stress. Okay? That's actually the starting point of our load line as it goes up, as it's drawn here. Because if now I have a little bit of applied stress, and it's on, off, on, off, on, off, my mean's increased by a little bit, and my amplitude now is increased by a little bit, and I'm up in this line. And when we're talking about a bolt, we're talking about loads going between 0 and something generally. And if that's the case, this line goes up at 45 degrees. Alright? Because that's the most sensible loading on a bolt. There might be some circumstances where you have a pre-tension plus a load that sort of stays constant, and so this could be a different angle depending on that, but it will take a lot of interpretation on your part to actually work that out, and I won't ask it. It will be something you actually do in reality if that's the case. Alright, so let's say now we've got more applied load going between 0 and something, amplitude goes up a little bit more, mean goes up a little bit more, we track all the way up until boom, we hit that, and outside of that we fail. Yeah. So this is our load line with the bolt. When you're going between 0 and something, A and M, difference is, gives you a 45 degree angle. Because of this, because FA equals FM equals FE max on 2. So that's for the applied loading, so FE. And the difference in this is FE. But anyway, hopefully you understand that. And we'll have a go at that in a second. Alright, factors of safety. Now, when you calculate a factor of safety on the right hand side of the Goodman line, so 1 on n, what that was doing was effectively, wherever you plotted your point, it was taking, assuming that that load, the potential load, can go from 0, 0 through that point up to a maximum. So it was a load locus that came from the origin through your point, and it calculated the ratio. So if I drew a line through that, my factor of safety based on that would be the ratio of here to here compared to here to here. Now we're not going through the origin anymore. We're going through this point. And like I said, that bolt will always have that load on it once you pre-tension it up. That's there for good. And so what we're actually interested in terms of a factor of safety when we're doing this sort of stuff is how much load can I apply to the bolt. You've pre-tensioned it, it's there, that's not changing. It doesn't make any sense for that to factor into our factor of safety because that's not really accurate. What we're interested in with bolts is what is the load? Can I apply double the load or triple the load? That's what the factor of safety is actually meaning. Alright, so the factor of safety we use for the bolts is just the ratio of this load line to the failure criteria. Alright, so how far up are we on that load line compared to how far up can we go? And that's easy to calculate because that's the same as the ratio of the sigma A value there and the sigma A value at intercept. So if you know your sigma A operational and you calculate your sigma A allowable based on that load line, the ratio of the two of them will give you the factor of safety. Okay? But not the sigma M, because the sigma M is this distance, and that's wrong. Okay? So there's a few little complex differences with bolts that you just need to get comfortable going through the process. So for the rest of this class, I'm going to do a really simple example, and then the tutorial will do a more complex example, and I'll put more examples up online for you to go through as well. Please read this section of the textbook because this is the hardest part that we're going to do for bolts. And I've just finished teaching you the hardest part, so it's just a matter of practicing it now. Cool. Oh, the last bit that I've got there is just, there are actually two ways to do that factor of safety. One way is that way, the graphics way, so just plot your operation point and then work out what the ratio is. Or if you have a load line and you know what that value and you have a factor of safety of 3, say, you know you need to come 1/3 up that line and then you calculate everything. So that's the kind of geometric interpretation way. The other way that works exactly the same is using an overload. So you remember that what I said was walking up that line is effectively dealing with how much load you can apply. So at 1, that's the absolute maximum load you can apply. Halfway up, that's, you can apply double that load and that kind of thing. So you can get exactly the same result for factor of safety at the beginning of the problem if instead of at the end you do that, 1/3 up the line calculation. If you've got a load that goes between 0 and something, you apply the factor of safety to the maximum value of force. It's called an overload. Okay? And so an example would be, if I give you a question of, force goes between 0 and 2,000 newtons, applied force, and you've got a factor of safety of 3, if you analyse for the load going between 0 and 6,000 newtons, so that's 3 times 2,000, and then you work out your operation point sitting right on the failure line, then you've got a factor of safety of 3. Alright, works exactly the same way. I don't care which way you do it, up to you. If you're given the forces, this is a nice easy way to do it right at the very beginning, and then you don't need to worry about factor of safety at the end. But again, this is an engineering thing, so use it carefully, use it pragmatically, and understand what you're using when you use it. Don't just randomly multiply your force by 3 and then calculate a factor of safety at the end as well. Okay? So it can either be done on the force or it can be done on the stressed locus line, but either way will give you exactly the same result. Okay, and I think your textbook talks about overloads a bit as well. So feel free to read further.
Just to clarify, so when you say it's going down by 3 on your AM diagrams and you wrote, that's just down by a factor of 3.
Yeah, so the ratio between B and A is 3, so A will be 1/3 the total length.
So I meant down with that one, you've gone down 3, you've just made it a third of the length, haven't you? Is that what
Yeah, so if that's 300,
that's
100, whatever. If you got that KM value of 3, which is effectively what you're doing. You're just putting a 1 on 3 out front of SN. So yeah, that goes down. Whereas when we did it on the stress, wherever your stress is, it's theoretically, moving it further up towards that line by a factor evenly in each direction. Yeah.
Yep.
Cool. All right. Example. Now, this example, I'm going to give you literally everything for, and then I'll work through it. And by everything, I mean I'm not going to require you to work out what the forces are, and I'm not going to require you to calculate the K values or the FI value or the SN value or any of that stuff. I'm going to give you numbers for those. Now, in an actual question, those are the first 4 pages of the analysis you're going to be doing, calculating all those different parameters. Okay? But in the interest of time, I'm going to give them to you. To be quite honest, that stuff's busy work and it's generally worth half the marks. So if you can just punch out an FI and a separation point and an SN, and you've got probably 2/3, probably 1/3 to half the marks for that question already anyway. Alright, so that's why I lay that stuff out first and do it well. Understand that and analyse the problem. Start putting lines on these things too. Alright, so you've given pretty much everything. This is the sort of stuff that you need to interpret out of some sort of a drawn problem. So what does the load fluctuate between, what are the K values, what's bolt size and material and all that kind of stuff. It's all axial load as an initial given everything, okay? So in this case, initial tension is given, but you can work out what the actual stress value of that is just by dividing that by the area anyway. I think it was like 90% proof load or something like that. Oh, actually, let's call that proof load. Alright, so let's find something. Right, factor of safety against fatigue failure is the first thing we're going to do. The second thing we're going to do is the largest FE max value. Right, and then so what is the maximum? We're given that we're applying 1,000 newtons currently. So what is the maximum values that can be applied if we had a factor of safety of 1? And what we might actually do is check for both separation and fatigue failure of the bolt. Okay. Alright, solution. Start with A. It's the first thing we do. What was that? FS? FS? Yeah, separation. So ordinarily we write all that crap down and actually have to work it out. We've got it all, but we don't have FS or FES yet, so let's calculate that. So FES equals, what was that? FI times KC, KB plus KC on KC, was that the equation? Fine. Something like that. That looks about, right, yeah, correct, cool. Alright. And so FI was 7320. This was 400E6 plus 2E9 on 2E9. And I got 8784 newtons. Alright, so are we to the left or the right of separation with our loading? Under? Yeah, we're under by quite a lot. In terms of separation, where are we at in terms of factor of safety or overload factor? Yeah, 8.7. Going on 9. So, we are, we could increase by a factor of 8 before we actually got separation. Now that says nothing about bolt strength or capacity, but in terms of overload and the factor of safety against separation, we're 8.7. Alright, so we have to use the full bolt equation. Thus, FB min equals Fi plus KB plus K, divided by KB plus KC times FE min. And our FE min is 0, so that means that equals Fi equals whatever that was, 7320. And FB max was 1000. So I calculate that at 7486.67 newtons. Right, so we don't have a lot of fluctuation going on. That 0 to 1000 external load is really only resulting in 7320 to 7486, so yeah, plus or minus sort of 100 newtons actually on that bolt. So you can see by having that initial tightening, for this case, you've actually decreased the amount of fluctuation on the bolt by a factor of 10. And remember how you trade off between mean stress and fluctuating stress on the AM diagram, that's actually a big deal. And so an additional advantage to having that pretension is because the change in fluctuation, particularly in between the 0 point and the separation point, because of the change in angle of that line, the decrease in slope of that line means that large increases in, or large changes in FE actually result in smaller changes in FB. I wonder whether I need to draw that to explain that a better way. Alright, so Alright, so if we're fluctuating between 2 points, right, we just project those up. And so the change, when you have an initial tension, compared to the change when you have no tension, is that. Yeah? And so by having that pre-tension there, not only are you having all of those other advantages based on the separation, the plate friction, all that other crap, but in terms of fatigue resistance, you're decreasing the amplitude. Alright? Now, you're increasing the mean stress, but you are decreasing that amplitude. So that's where that trade-off actually comes, and there is an advantage from a fatigue resistance standpoint as well. You guys feel free to go and, throw a couple of numbers in this sort of stuff and see where you lie and what the factor of safety for different circumstances of pre-tension are for the same amount of force. And it's interesting, it's completely counterintuitive. It confuses the hell out of me every time I haven't done it for a little while and I have to go back and redo it, but you do have advantages for that extra.
Does that mean the more you tighten it, the better, or is there a point where it's not?
It's not a linear relationship in that respect, but the pre-tension does help you in certain circumstances within a sort of range. So it's not just that you put force on the bolt and everything goes to hell and it's worse. So we look at it and just the normal engineering process would be more force equals bad. But what I'm sort of trying to show there is more force doesn't necessarily equal bad, because by putting that pre-tension on it, it changes the actual loading characteristics of the system. And so that, even if it's not an advantage, it's not a disadvantage. It's not the sort of disadvantage that you might otherwise expect it to be. So if nothing else, you get that extra load for free, and then you get all of the other advantages on top of it. But it sort of depends on where you fall in the loading. Alright, so if we have FB max and FB min, we can calculate sigma max and sigma min. P on A, which is 7486.7 divided by 36.6, and to convert 36.6 to meters, just stick an e to the minus 6 on it. Very good with that? Easy. And that ends up being 204.55 megapascals. And sigma min, same deal. 7320 on 36.6 E minus 6. And I get that as 200 flat. Theoretically should be the proof load. Alright, last thing we need to do before we can chuck it on the AM diagram is calculate A and M. So M is obviously the average between these two numbers, and A is the half the difference. So if we just look 204 and 200, what's the average going to be between those before I even use an equation? 202-ish somewhere, so that's ME. And the difference between them is 4.5, so the amplitude is up that, so it's going to be 2 point something, so a tiny little amplitude. Uh, 2.275 megapascals. And sigma M is the average. so now we have an operation point and we can plot that on an AM diagram and we can work out a bunch of things from there. Alright, so our SN value is 65. We're using SP here. And SU is 450. Now, the value to use here, if you don't have with bolts, I prefer that you use your proof load here. Remember that we said static failure and bolts we use the proof load? The reason we have previously on an AM diagram the yield line is because the yield line deals with static failure. Alright? So if we carried along this line and hit yield, that's equivalent to our static failure criterion equation. Alright? So the fact that ordinarily, for any other component, yield is dictated by our static failure criterion that we use for shafts, wheels, etc. For bolts, our static failure criterion for bolts is that we're under proof load. So it makes perfect sense that instead of yield on this diagram, we use proof load on this diagram. And once again, as with everything engineering, I've seen it both ways. Okay? So yield and proof are relatively close together. Proof is a little bit more conservative. Proof is what you've actually tested the bolt at, so that's why I use that. You wouldn't be wrong to use yield, but now that I've told you to use proof in this class, please use proof in this class. Okay. But yeah, use engineering judgment. Alright, so our intercept starts here at sigma, whatever the factor of proof load, sigma I, and that's 200. Which you can calculate, firstly we know from sigma min, but secondly you can calculate just by taking Fi and dividing it by AT, which is 200. Alright, and so that's where we start on our load line. We are loading between 0 and something, and so that tells us we're going up at a 45-degree angle, so our load line is up like this. And we have some operation point somewhere between those 2 points, hopefully somewhere between those points. If it's outside of those points, then obviously we're failed. And our operation point is what we just calculated there, X value 202.275 and Y value 2.275.
Sorry, Dave, where did the 200
Which 200?
signal
So 200, so let's say, whatever this is, what's that, 2/3? So the question would have asked for, 80% of roof load, 70% of roof load, or whatever, is the initial force. So the initial force of 7,320, probably would have been given, you would have been given 30% of roof load, 90% of roof load, you would have taken your roof load, multiplied it by 0.9, and then that's that value, and then multiplied by area, and that's this value. Yeah, so that's whatever our pretension stress is.
Alright.
So whatever you tighten it up to in terms of stress, that's it. Which also just happens to be our sigma min. So the sigma min, if you don't have any applied stress, if you're going between 0 applied stress and something, 0 applied load and something, then our minimum stress is actually whatever we're tightening it up to initially. That's again the roof load. So if we knew the roof load, we wouldn't have theoretically had to calculate this, but we did just to go through the motions. Silly sense. Sorry. Cool. All right. So we're going to do a few things. Effectively, we want to know this ratio to this ratio to answer A, and then B, we want to know what the actual force is at that point. So our job is to work out that intercept, and that intercept could be with the Goodman line and it could be with the yield line. What am I analysing? I think I'm analysing just the Goodman line, but you guys can analyse both. Now with bolts you always have to analyse both, so we'll we'll do both. Remember that? Yep, we'll do that. Alright, so let's do the Goodman line first. We'll work out an equation to this line. I'll just do the two equations to the lines and solve it method. You can do it however you want. You can throw it into whatever. Remember that the Goodman line doesn't have that one on n anymore because we've already dealt with n elsewhere, or we're calculating n. And that's the one on n in the Goodman equation assumes that the intercept is here. And so we don't use that for bolts. So the equation to this line is its slope, which is 1, times x, which is sigma m, plus the intercept, which is 202. So the first thing we have is sigma A equals sigma m minus, sorry, the intercept is 200, minus 200 megapascals, so E6. And that's our first equation, one load line. And the second equation is the equation for this line, which is sigma A equals negative 65 on 450 sigma m plus 65. Alright. Alright, and if we were to do the yield line, we would have the same load line equation, sigma A equals sigma m minus 200 E6, and the yield line equation is sigma A, because it's at 45 degrees down, it's just minus 1, and the intercept is 300. Alright, this side of the room, you're doing Goodman line. This side of the room, you're doing yield line. Or, yeah, it's proof load line. Spend 2 minutes on that and then we'll get a solution, we'll be done.
So what's the difference between the top half of it?
The top half is, I probably should write that, shouldn't I? This is the Goodman. And this is the proof load line. Alright, and once again, two equations 1 and 2 to simultaneously solve. Alright, so these things are pretty easy when you just say mx plus c. Whatever your slope is and whatever your y-intercept is, you have two equations to two numbers. And we go, Goodman side, you got a value?
31.6 and 231.6.
6 megapascals for A and 231.6 megapascals for me. Good. Yield side? I don't know, I can calculate this. So, A alternating is 15 meg. Sorry? 50, 50, that sounds better. 50 megapascals. And what's sigma m? 250 megapascals. Excellent. Yeah, that sounds right. Cool. So which one's more critical? Goodman. Excellent. All right. So now, very quickly in our last minute. Alright, so A, therefore N equals sigma A allowable on sigma A operational equals 31.5, what was it, 31.5 or 6 something? Yeah, 31.6 divided by 2.275, and I get 13.87. So is that more or less than our factor of safety against separation? Remember the factor of safety, what was that, 8.7? Factor of safety against separation? So you would probably say, and separation n equals whatever it was, 8.7 I think it calculated as. So that one's the more critical. Alright, now the last thing was, B was what was your allowable force. It'll be in the notes so I won't write it up, but sigma A and sigma M, if we add them together we get sigma max. And that sigma max is just equal to force max divided by the area of the bolt. So the area of the bolt, bring it on back, and that'll calculate your maximum force, or your maximum stress that gives you theoretically. So I'll have the notes and you guys can read that, but we've gone over time already, so please read that last little bit of the notes and then we'll be good. Then we have a proper example of this on Monday and we can work through it. Okay? Sorry, that was what I was trying to say. So you calculate the maximum force of the bolt just by rearranging that equation, yeah, multiplied by A and whatnot, and then you need to calculate the actual allowed, the externally applied load that's allowable. And so that depends on whether you're to the left or the right of that separation. So that was the last one. But that's the numbers. Yeah.